Everyone, in this video we are going to go over ring opening of epoxides. So let's just start with a really simple epoxide. And let's say we have a strong nucleophile, like the hydroxide ion. And let's just make a note that this is a strong nucleophile. The nucleophile is going to attack one of the carbons on the epoxide, and that's going to open up our ring. So now we're going to have a negatively charged oxygen opposite our nucleophile. And then in the next step, actually let me draw equilibrium arrows here. In the next step, we're going to use water to protonate the negatively charged oxygen. Okay, now this would be considered under basic conditions. So we don't have any acid really present. Water is neutral, and we have our strong nucleophile there. So this would be our mechanism for basic conditions. So you can do this with really any strong nucleophile. So your textbook has a cool chart that shows all of the different possible nucleophiles you could use. So for instance, maybe instead of the hydroxide ion, we use an alkoxide ion, followed by water to protonate. So then we would add OR opposite the OH group. You could also use cyanide. So then that would add the cyanide group opposite the alcohol. We could use a sulfur ion. We could also use a Grignard reagent. So that will count as a strong nucleophile. And this one is cool because then you're just adding more carbons onto your chain. So you could consider this almost an alkylation in a way, just a different way of adding carbons. And then finally, you could also add a reducing agent like lithium aluminum hydride to add a hydrogen opposite the alcohol. All right, so lots of different options here. And again, these are all strong nucleophiles. Now, what if we're under acidic conditions? So what if we have an acid present? So let's use our simple epoxide again. But this time in the first step, we're going to add acid. And that could be sulfuric acid, for instance. So the oxygen this time is going to grab onto a proton and become positively charged. And then in the next step, we'll add our nucleophile, which this time will be a weak nucleophile, such as water. And then we'll end up with our alcohol opposite the nucleophile. And in this case, we have to deprotonate. and we get our product. All right, so the mechanism under acidic conditions is slightly different from the mechanism under basic conditions. So here we're protonating the oxygen first, and then we see nucleophilic attack, whereas under basic conditions, the nucleophile attacked first, and then we protonated. Okay, now one other thing that we need to consider is what's called regiochemistry. So where would a nucleophile attack if we have an asymmetric epoxide? So for instance, let's say we have our protonated epoxide here. And instead of being symmetrical, let's add a methyl group on one side. So now this is asymmetrical. Okay, so where would the nucleophile attack? So let's highlight the left carbon in blue and the right carbon in red. Okay, so how would we characterize the blue carbon? Is it a primary carbon, a secondary carbon, or a tertiary carbon? So it's only bonded to one other carbon, so that would make it a primary carbon. What about the red carbon? Is that primary, secondary, or tertiary? Secondary. Okay, now in this case, we want to consider the sterics. So the nucleophile is going to attack the less hindered side. So that would be the primary carbon. So let's make a note. Typically, the nucleophile will attack the less substituted carbon due to sterics. And this is true for both acidic and basic conditions. So let's see, let's make a note somewhere. Okay, but what if we have a tertiary carbon? So let's give that right-hand carbon 2 methyl groups this time. So again, the left-hand carbon is still a primary carbon, but now the right-hand carbon is a tertiary carbon. So in this case, under acidic conditions only, the nucleophile is going to attack the tertiary carbon. So why is that? It seems kind of arbitrary, but if we think about the transition state of this molecule, or this reaction, I should say, it actually makes a lot of sense. So let's draw the transition state in brackets. Okay, so let's say the nucleophile is coming in to attack the tertiary carbon. So the oxygen is now partially positively charged because its bond with the tertiary carbon is breaking. And the nucleophile is partially negatively charged. And let me finish off these brackets here with a transition symbol. So in this case, we want to consider the electronics. So those two methyl groups that are attached, they're stabilizing the tertiary carbon as bonds are forming and breaking. And that's again due to hyperconjugation. Okay, so under acidic conditions, the nucleophile will attack the tertiary carbon if available. So really all you have to remember is that the majority of the time with epoxides, the nucleophile will attack the less substituted carbon just because it's more available. It isn't as bulky. But if you have acidic conditions and you have a tertiary carbon, then the nucleophile will attack the tertiary carbon because it's the more stable carbon due to hyperconjugation. So that's really the only part you have to remember is, again, acidic conditions and tertiary carbon. Otherwise, the nucleophile attacks the less substituted carbon. Okay, so let's go over an example just so we can get some practice with this idea. All right, so let's give an alkene here, and it's kind of a simple alkene. And let's say we add MCPBA, and we have acidic conditions. What product would we expect? So if you want to pause the video and try this on your own first, you can. And when you're done, you can unpause the video and we'll go over it together. Okay, so let's see. We know that if we add MCPBA, we're going to form an epoxide across the double bond. Okay, and I'm going to number my carbons, 1, 2, 3. Okay, so if I'm adding my epoxide across the double bond, I still have one carbon off to the side. So that's going to be a methyl group, and I'll just draw it as a wedge. All right, and then everything else that was bonded to the double bond is a hydrogen, so I'm just going to draw those in. You don't have to draw those hydrogens, but sometimes I like to see everything that's bonded. Okay, so then we're under acidic conditions, so that means that we'll also protonate that oxygen on the epoxide. And I'm kind of skipping the arrow pushing mechanisms here. I'm just kind of drawing what the intermediate would look like. All right, so now let's figure out, okay, if we add a nucleophile, what would our product look like? Which carbon would the nucleophile attack? So if you want to pause the video again and figure out where the nucleophile would attack, you can. And then when you unpause, we'll go over it together. Okay, so which side would the nucleophile attack? Let's see, so we have our blue carbon and our red carbon. And how would we characterize the blue carbon? Is it primary, secondary, or tertiary? secondary. It's attached to two other carbons. What about the red carbon? Is that primary, secondary, or tertiary? It's primary. It's only bonded to one other carbon. So which one would the nucleophile attack? The primary carbon, because we don't have a tertiary carbon available. All right, so that would open up our ring, and we would end up with an OH group off to the upper left, and then our nucleophile down below, and then we've got our hydrogens on the right-hand carbon, and then we have a methyl group and a hydrogen on the other carbon. Okay, so in this reaction, we were under acidic conditions, but we didn't have a tertiary carbon available, so the nucleophile attacked the less substituted carbon. So let's write that down. If no tertiary carbon is available under acidic conditions, the nucleophile attacks the least substituted carbon. Now, what if we were under basic conditions? So let's say that oxygen is not protonated. Where would the nucleophile attack? The less substituted carbon again. So under basic conditions, the nucleophile always attacks the least substituted carbon. Okay. So let's just kind of summarize all of the possible reactions. And what we're going to do is kind of split this up into acidic conditions and then non-acidic conditions. So let me draw an epoxide here in the middle, and we're going to give it a tertiary carbon. Okay. And then I'm going to split this map in half. And we're going to say that everything above that line will be under non-acidic conditions. And everything below the line will be under acidic conditions. Okay, and then I'm just going to draw some reagents here. So we've got SR minus, we've got CN minus, let's put in an alkoxide, and we'll also put in a Grignard reagent. And then down below, let's add just acid. And some other reagents here. Okay. So what I would like you to do is draw the products for each of these different sets of reagents. And again, you're starting with that epoxide that I drew. So if you want to pause the video and figure out all of those different products, feel free. And when you unpause, we'll draw all of the products together. All right, so remember that if we're under basic conditions or non-acidic conditions, the nucleophile will adds to the less substituted carbon. And that is always true under non-acidic conditions. And again, that's due to sterics. So looking at our first set of reagents, Sr minus and H2O, the Sr minus nucleophile would attack the less substituted carbon. So that is the one on the left. And we'll just say that we also protonated the oxygen at the end. And then don't forget those two methyl groups on the more substituted carbon. And then this is really going to look the same for all of the other products, except we're just switching out that nucleophile. All right, so that looks really similar, but instead of Sr, we have Cn for cyanide. In the next one, we're just going to add in OR. And on our last one, we're just adding an R group, so some sort of alkyl group. So again, here, everything is adding to the less substituted carbon because we're under non-acidic conditions. Okay, so now remember, under acidic conditions, the nucleophile adds to the tertiary carbon if available. Otherwise, it will add to the less substituted carbon. All right, so the more substituted carbon is our tertiary carbon. So that means that, again, the nucleophile will add to the tertiary carbon under acidic conditions. Okay, so if the nucleophile comes in and attacks the purple carbon, the tertiary carbon, our first product where we add H3O plus will look like the following. So this one is a little hard to tell where we added the group, so let's look at our next one. So again, we're under acidic conditions, so that acid is going to protonate the oxygen first, and then SRH will come in and eventually will deprotonate the sulfur group. All right, and then on to the next one. In this case, we're going to add OR. And in the last one, we're actually going to add a halogen to the tertiary carbon. So this is really great because you can kind of control where a group adds to your epoxide. So you can create acidic conditions to make sure that your nucleophile adds to the more substituted carbon, or you could keep things more basic and add the nucleophile to the less substituted carbon. All right, now one last little note. All of these acids that I wrote, these catalytic acids in brackets, those are usually sulfuric acid, phosphoric acid, oh, that should be a P, or a tosyl group with OH on it. All right. So in the next video, what we'll do is go over some more examples with epoxides, and we'll also practice figuring out where nucleophiles will add. So either to the less substituted carbon or the more substituted carbon. So I will see you then.